Hello and welcome back to the AI 900 course certification. And I'll be going through this video. I'll be going through the fundamentals of machine learning. If you're following along, don't forget to go through the playlist where I've gone through the first video, that is the fundamental AI concepts, and the next one is the fundamentals of machine learning. And then we will move to other modules as well that involves computer vision as well as the natural language processing, along with the document intelligence features in Microsoft AI. And this is part of a study guide which you will be prepared for attempting or giving the and passing the AI 900 Microsoft Azure AI fundamental exam. So let's get started. So we'll start off with the fundamentals of machine learning. Most of the course content is theoretical based. I'll be just sharing some information regarding machine learning and the concepts related to that. So let's get started. Machine learning is the basis of most modern artificial intelligence solution. So a familiarity with the core concepts on which machine learning is based is an important foundation of understanding the artificial intelligence. So in this one I'll be going through the core concepts as well as what are the different types of machine learning, as well as I'll be describing the machine learning models as well, and along with the core concepts of deep learning. Plus we will be looking in to the glimpse of automated machine learning in Azure machine learning service. So let's get started. So machine learning in many ways is an intersection of two disciplines. One is the data science, the other one is the software engineering. The goal of machine learning is to use data to create a predictive model that can be incorporated into a software application or a service. So it goes through to achieve this goal. It requires collaboration between the data scientists who explore and prepare data before using it to train a machine learning model, and a software development who actually integrates the model into application where they are used to predict new data values there. So the core concepts of machine learning starts off with the definition that machine learning is a subset of AI and that enables system to learn and improve from experience without explicit programming. And it originates from statistics as well as mathematical modeling of data. So the fundamental idea of machine learning is to use data from past observation and predict unknown outcomes of the values. And basically, the model, it learns itself from the previous experiences and learning, and then go through the future prediction as well. You don't have to worry about if you're not a mathematical expert, but this one will be going through all the processes of the machine learning, as well as we'll go through types as well. So there are three types of learning as shown. One is the supervised learning, which means that we label the data about some concepts, and then the machine learning platform learns from the data and predict the future. As well as the second one is the unsupervised learning, means that we don't label the data, but the model uh, find the patterns in the unlabeled data. And the third one is the trial and error thing, which means that we keep on go through some of the variables and predict based on the results, and then we capture the best possible outcome in the results as well. So the next one is the actual application. Because machine learning is based on mathematics and statistics, it is common to think about machine learning models in mathematical terms. So basically, a machine learning model is a software application that encapsulates a function, which is the language of mathematics, to calculate an output based on one or more input value. So the process of defining the function is known as training, and after the function has been defined, you can use it to predict new values in a process called inferencing. So basically, this is a variable that we are declaring, and then we are doing some operations, and then creating a function of the mathematical things that to get the results. So it an observation, this is a training kind of a data that consists of parsed observation. In most cases, the observation include the features, and these features are being observed, and then there are some known values of a thing you want to train the model, and predict, which is the unknown value. So in mathematical term, you often see the feature referred to using a variable called x, and the label is referred to as y. Usually an observation consists of multiple features as well as multiple values, like if you see x1, x2, x3, and then y. So these are the things that go through the process and define the function. I'm giving you an example. So for example, let's take an example of an ice cream sales scenario. So our goal is to train the model that can predict the number of ice cream sales based on the weather. The weather measurement of the day means that involves temperature, the wind speed, as well as the rainfall or thunderstorm prediction. So these would be the features, and the number of ice cream sold would be the label, that is the variable y. So this is one scenario. We have to go through defining the features as well as defining the results as well in order to move forward. In continuation, we apply the algorithm, that is the defining of features and values. We then model and then function, use the function, and then basic principle is to try to fit a function to the data in which the values of the feature can be used to calculate the label. Here, if I define this thing, an algorithm is applied to the data to try to determine the relationship between the feature and the label or the value, to generalize that relationship as calculation that can be performed on X to calculate Y. The specific algorithm depends, on the kind of the predictive problem that we are trying to solve. But it's it's basically is to try to fit a function, as I mentioned earlier. So when there is the algorithm is set, the result of the algorithm is a model that encapsulate the calculation derived by the algorithm as a function. So for example, this function is y is a function of X, and we define as a function. But then when once this training phase is complete, the train model can be used for inferencing. The model is essentially a software program that encapsulates the function produced by the training process, and then you can input the set of feature value as well as receive an output predictive value. We will be discussing this in our further future discussion, modules, as well as this one as well. But because the output of from the model prediction that was calculated by the function, the output can be considered. So this value and this result can be a variable or another value as well, or can be a predictive value. If it is a predictive value, then it is labeled as y hat, which is the for example, which showcase that this is a calculated value rather than the observed value. So we'll move on to the types of learning, like supervised machine learning. A supervised machine learning is a algorithm in which training data includes both feature value as well as the label value. This means both y and x to be included. This machine learning type is used to train models by determining the relationship between the feature and label in past observation, so that unknown label can be predicted for feature in the future cases. So the classification of supervised machine learning is basically a regression form, which is label I mean, in which the label is predicted by the model based on a numeric value. So for example, the number of ice cream sold in a given on a given day based on temperature or weather conditions, and like wind speed. So for example, the other example is the fuel efficiency in kilometers per gallon of a car is based on engine size, weight, width, and height and length, etc. So this is one type where they're only the numerical value is given. The second one is a form of classification, which is a form of supervised machine learning, in which the label is represent the categorization, and the categorization of or a class, like the so in binary classification, the label determines whether the classification or the observed item is an instance of a specific class. So basically, this one will result. If you divide, for example, two things, like the whether a condition is met or not, or whether the condition is false or true. This might be the prediction of a single class thing. For example, in the bank account, or a credit card customer will default on a credit card bill based on income, credit history, or not. So this is the positive or negative prediction based on some of the inputs or some of the features that we input in the credit card customer systems. The next one is the multi-class classification. It is an extension of binary class classification to predict the label that represent one or multiple possible classes. So, for example, the species of a penguin multiple based on the types of measurements and physical appearance. So unsupervised machine learning, it involves training module using data that consists only feature values without any known results or known labels. So this it basically determines the relationship between the features of the observation in the training data. So like similarly similar objects classification as well, without any types to be defined. So for example, this is an extension which is called clustering. It is the most common form of unsupervised machine learning. It identifies similarities between the observations, like a group of similar flowers based on their size, number of leaves, or number of petals. So this identifies a group of what you call it identify a group of similar customers and similar flowers based on their properties. So this is called clustering. So this clustering is somewhat similar to the multi-class classification, because it categorizes the observation into a discrete groups. The difference between the clustering and multi-class classification is that the classification it categorizes the observation into some of the discrete groups, but you already know the classes or types as well. But in clustering, there's no previous known clustering label, and the algorithms of the group of data observed based on purely based on similarity of features, as well as similarity of features, like in the example of roses, the types as colors, as well as the number of petals and leaves as well. So next up, we'll move to the type of supervised learning, which is regression. And the regression model are trained to predict numerical label, as mentioned. The process for training the regression model involves multiple iteration in which you use an appropriate algorithm. So this basically regression, this is how it works. So this diagram shows four key elements of the training process. We have to split the data to a randomly to create a data set. So with which we will be we'll be training the model, um, while holding the subset of the data that you will validate to train the model. So we are keeping this one as the first step. Then in the second step, we are using the algorithm to fit in the training data to the model. So we'll use some algorithms to predict that, and then we'll just validate the data with the original data as well, what we have. So this will be the testing of the model by predicting the labels for the feature, and then we will be also comparing the actual with the model that is predicted to give some differences. And then the predicted and actual labels value, we will just find out some differences, and to calculate metrics that indicates how accurately the model predicted the validation data. So after each training or validation or evaluation, you can repeat the process with different algorithms and parameters until the acceptable evaluation metric is achieved. So let's head to the ice cream example. So this is the ice cream sales scenario, and we are exploring this based on the numerical label and based on the single feature, like the temperature versus the ice cream sales. So in this way, this is the input, or this is the feature that we want to test. So in this one, this is the it's a single variable, that is the temperature. And so this is the average temperature or the maximum temperature at a given day. It is in Fahrenheit. And then we have the label value that is showing the number of sales, and we want to predict, and we want to take some historical data to include the daily temperature versus the ice cream number of ice cream sold. So what we'll do, we'll split the data, and using the subset to train the model. And the training data set involves randomly selected values, and then we go to the we go to the applying of the algorithm to our training data. We can also plot the coordinates of xy values to see what is what does it look like graphically. So for example, we start off with linear regression algorithm, which works by deriving the function that produces a straight line through the intersection of x and y value, while minimizing the average distance between the line and the plotted points. So this line actually represents the function of the slope of the to calculate y at a given point of time. So it's basically saying that when x is 50, y is 0, and and so on. If you're going through this, and if we increase 5 degrees, there the y also increases. So this means that if x is 55, then y is 5, and when x is 60, y is 10, and so on. To calculate the value of y from a given value of x, we just use the value minus 50. So this means that we have the function of x, which is the y, which is the function of x, is x minus 50. That is the formula that we have given. So for example, the weather forecast tells us that it will be 75 degrees. Then we will have the value shown as in this value is showing around 25. So this means that we are using x minus 75 minus 50 is 25. So it is giving a closer value. So this is the one that we predicted. So this is the input value. Now we are validating the value with the actual sales, and this is the predicted sales that is showing as y hat. And on each temperature, it is showing some predicted sales around it. We can also this is the formula that we are using, and we can also plot this based on the differences between the predicted value and the actual value. So y represents the golden ones, as well as the pinkish or the magenta color represents the y hat, which is the predicted value. And we can give the differences between the evaluation in the regression model. So this means that we can calculate some of the values, or some of the calculations based on the evaluation metrics. There are some of the calculations methodology that we can use, like mean absolute error, mean squared error, root mean squared error, as well as coefficient of determination. I'll go through one of them, one by one. The mean absolute error gives us a variance. In this example, like how many ice cream of each prediction was wrong. It doesn't matter if the prediction was over or under. So, for example, -3 or +3 both indicate the variance of 3. This metric is known as absolute error for each prediction and can be summarized as whole as mean absolute error. So this means that there are some differences that is showing. So 2, 3, 3, 1, 2, 3, and this is we are just dividing it by 6 to get it 2.33, which is the average. The next one is mean squared error, though. So the mean absolute error takes all discrepancies between predicted and actual labels equally, but it may be more desirable to have a model that is consistently wrong by a small amount, that one that makes fewer but larger errors. The other way is to amplify the number of errors by squaring the individual errors and then calculating the mean. So this means that we are just squaring each value and then taking out the mean. With this will be called mean squared error. So in this example, the mean square error is 6. So we have amplified the result to get up the magnitude. So it actually doesn't represents the what do you call it the actual number of quantities measured, because it amplifies the result, or it increases the result. So we cannot say that there's a 6 ice cream difference in the calculation. So we just take a square root of it, so that in order to come back to the prediction or the number of ice creams, so it comes up with 2.45 ice creams as a result of the mean square. So all of the matrices so far compare the discrepancies between predicted and actual values in order to evaluate the model. But however, in reality, there are some natural random variance in the daily sales of ice cream that the model takes into account. In a linear regression model, the training algorithm fits a straight line that minimizes the mean variance or between the function and the known label values. So here comes coefficient of determination, which is R2, and which means it's R squared generally. So that measures the proportion of variance in validating the result that can be explained by the model, as opposed to some anomalies to validate the data. So it's so it can unusual number of ice cream sales because of some festivals or school holidays. The calculation of R square is more complex than the previous metrics. It compares the sum of square of the differences, they divided by the mean, the actual value of the squares. So it looks a bit complicated, but this is the fancy of the machine learning algorithm or the machine learning tools to calculate this metrics. The important point is that the result, the value is in between 0 and 1, that describes the proportion of variance explained by the model. In simple terms, the closer to 1 the value is, the better the model fitting the validation data. In the case of this one is showing 0.95, which is a bit of closer, we can achieve more, but this is the end results that is showing. So next one, so the matrix they define and then the calculation define are the commonly evaluated regression model. In the real world scenario, a data scientist will use an iterative process to repeatedly train and evaluate a model. It depends on feature selection, preparation, choosing which variables or which feature to include in the model, and calculations applied to them help ensure which one is a better fit. Then we will use for the algorithm selections. So currently we explored linear regression in the examples, but we can use other regression algorithms as well. And we can also use algorithm parameters like numerical settings, behavioral settings for more accuracy. And after multiple iterations, the model that results in the best evaluation metric can be acceptable for the specific scenario selection. Next, we will move on to binary classification. This is basically a part of classification, and this is like regression, but it's part of the supervised machine learning technique. It follows the same iterative process of training, validating, evaluating the model, but instead of calculating numerical values like a regression model, the algorithm is used to train classification model calculate the probability values for the assignments or the class assignments in the evaluation. Binary classification algorithm are used to train model that are predict two possible labels for a single class. So for example, predicting a true or false, or zero or 1 in the data observed. So basically it just gives validations whether a particular item is belonging to a particular result or not, or particular class or not. So basically, for example, if we consider this example, the blood glucose level of patient, to predict whether or not the patient has diabetes, we just give some probability, value between 0 and 1, the to give the possibility as well. So for example, this is the blood sugar glucose level of patients, and the prediction, the giving thing is that whether the person has diabetes or not. And to train the model, we will use the algorithm to fit the training data to a function that calculates the probability, and then this probability can be said that if a patient will have so for example more than zero point 0.5, probability will be increased when the patient will have uh, higher glucose sugar level higher than some sort 85 or 90. So this means that we can give a particular results based on the input. There are many algorithms that can be used for binary classification, such as logistic regression, which derive the S shape functions, which is the values between 1 and 0, like the ones in there. So basically, the function produced by the algorithm describes the probability of y for a given value of x. So it's saying, the function of x is the probability of y equals 1 or x. So for the sixth observation that we have in the previous slide, that is this one, we will have for the sixth observation, we know that y is definitely true when the probability for the observation is 1. And for those the other three, we know that y is definitely false because the probability is 0. So this S-shaped curve describes the probability distribution, so that plotting a value of x on the line identifies the corresponding probability that y is 1. This diagram also includes a horizontal line that indicates the threshold at which the model based on the function will predict true or false. The threshold line at this stage is zero point 0.5. For any values at this point or above, the model will predict true, while or any values below this point will the model will predict false. So a patient with a blood glucose level of 90 will result in the probability value of zero point 0.9, which is higher than the threshold of point. This means that it will predict as true. So even 85, for example, taking as zero point 0.5 or something, 86, so it will give us a threshold of the values in this S curve. So we are basically training a binary classification model by applying some random subsets as well. So here are the values that we have put up, and the regression value will be given by the model itself, and these values are based on the actual diabetes diagnosis or the predictive diagnosis. So based on this, whether the probability calculated by function above or below the threshold, the model generates a predictive label of 1 or 0. This is basically a classification which is given, or binary means that it's either given 0 or 1. So we are calculating or comparing actual, which is the value of y, versus y hat. So next, we can compare, as we have done the comparison between the predicted label with the actual, and it says that this visualization will showcase a matrix which is the number of correct or incorrect prediction of each possible class label. So when the y and y hat is 0, there are true negatives. When y hat is 1 and y is 0, this is false positive. Then we come for false negative as well as true positives. True positive is y is 1 and y hat is also 1. So this is true positive. So now this confusion matrix, we can calculate the results as well, with taking into all values like true negative, false positive, false negative, as well as true positives. And this is the accuracy that we can check. So we already will be taking true negative and true positive. So this means we are taking it as a numerator and dividing it by the by the complete results of the taking into the denominator. So in this case, 2 and 3, and then 2 plus 1 plus 0 plus 3 is 5 divided by 6 and 0.83. So for our validation of the data, the diabetes classification model produced correct predictions 83% of the time. Accuracy might initially seem like a good matrix to evaluation of the matrix, but consider this, 11% of the population has diabetes. You could create a model that always predicts 0, and it would achieve the accuracy, or achieve the accuracy of 89%. But what we really need is a deeper understanding of how the model performs, predicting 1 on positive cases and 0 on the negative cases. So going to recall, or comparing the number of patients who have diabetes and how many did the model predict to have diabetes. So our value basically correctly, positive 1 divided by the true positive and false negative, that 75% patients who have diabetes have diabetes actually. So this is the formula for recall. Um, this only focuses on positive cases. The other one is precision, and the precision, in other words, is what proportion of patients predicted by the model to have diabetes actually have diabetes. So the precision is 100% in this case, which is predicted by the model to have in fact have diabetes. Then next calculation, we go to the F1 score, and then F1 score is a combination of the recall and precision. And the formula for F1 score is the 2 multiplied by precision into recall divided by precision plus recall. And in this example, we are just taking values from the confusion matrix and then evaluating 86% as an F1 score. And what we'll do is we will put these scores into the curve, and so this basically gives a binary classification and performance as well. So this recall plus the precision one and F1 scores, we are putting it in the plot. So this recall formula is also called true positive rate, where and then the formula inverted to that true positive rate is the false positive rate. And we already know that the true positive rate of the model threshold of is 0.5 to 0.75, and we can use this as a formula to calculate the false positive rate as well. So it gives us false positive as 0, and true positive as if we go back here, it will give us 0.75. Sorry, yeah, this one. We can tweak the values of true positive rate as well as the false positive rate as well to see and compare different scenarios. But it always gives it produces area under the curve. So how this area under curve works is that it is based on receiver operating characteristic curve, which compares the true positive rate, which is 0.75 in this case, and false positive rate, which is 0. So it plots the value here. So and then a diagonal line is created from the false positive to true positive. The next we will move on to the multi-class classification, and it is part of the it is used to predict to which multiple possible classes an observation belongs. And it is part of the supervised machine learning technique, which follows the same iterative train, validate, evaluate process, uh, same as the regression and binary classification. So if you take examples of observation of penguin in which the flipper length of each penguin is recorded, and we predict the species based on that flipper length. So this multi-class classification algorithms are used to calculate the probability values of multiple class labels. So it predicts basically the most probable class for a given observation. So if these are the penguin species types based on the flipper length. So this is the entrance of the data, and then we'll do the to train a multi-class classification model, we need to use an algorithm to fit the training data to a function that calculates the probability value of each possible class. So there are two kind of algorithms we can use: the one to rest algorithm, one versus rest, or multinomial algorithms. So one versus rest train a binary classification function for each class. In the each calculating the probability that then observation is an example of a target class, means each function calculate the probability of specific species. So each algorithm basically produce a function that calculates the probability value between 0 and 1, and a trained model is used. This algorithm predicts the class of a function that produces the highest probability output. So it takes the highest probability and then it post it as a result. While in contrast, the multinomial algorithm, it's an alternative approach which creates a single function which results in the multi-value output. The output are the array of values, it contains multiple distributions upon all possible classes. The score for each class, which when total will add up to 1. So for example, this gives a probability of 0.3, 0.4, and 0.3 again. So the function total value output value would be 1. So the flipper length versus the actual species value as well as the predicted species, which is the y hat, gives a confusion matrix as well to give us some values of false positive and true negative as well. So next we will move to the evaluation, and this evaluation of multi-class classification, from the confusion matrix we determine the individual matrices as well as the accuracy versus recall, precision, and F1 score. So prediction, the overall accuracy, we will just add up all the metrics related to the overall precision metrics as well as the recall metrics. and we come up with the F1 overall score by multiplying and dividing with the actual precisions and recalls to give go up as an 86% score. Next, we will move on to clustering, which is a form of unsupervised learning, and where the observations are grouped into clusters based on similarities in the data value or the feature. Um, this unsupervised learning, as mentioned previously, as that we will it doesn't make use of the previously known label to train the model. So in contrast with the clustering model, the label is the cluster to which the observation is assigned. So the species as well as the types of diabetes based on that. So we'll go on to the flower examples. So there are no known labels in the data set, and it's just two features that are. So the botanist will go through and identify different types of species of flower just to group similar flowers together based on number of leaves and petals. So these are two values that are there, and observations, and then we train the clustering models using some multiple algorithms. One of the most commonly used algorithm is k-means clustering, which consists of the following steps. So for example, the first step would be the feature values are vectorized to define n-dimensional coordinates, like this one. So we define based on x1 versus x2. So in this way, we have two features we have plotted accordingly: the number of leaves and number of flowers. So it is a two-dimensional space. The second step will be you decide how many cluster you want to use the group of flowers. So we call the value as k. So for example, to create three clusters, we will use the k value of 3. So the k points are plotted at a random coordinate. These points become the center points for each cluster. So they are called centroids. So like this, these are the centroid clusters are pointed out. Next step would be that each centroid is moved to the center of data point to assigned to based on the mean distance between those points. Next would be that after the centroid is moved, the data point may now be closer to the different centroid. So the data points are reassigned to cluster based on the newest closed centroid. So this means that we have changed the type or the the angle or centroid as well to go through the closer based on the closest centroid. Next step would be the movement and the cluster relocation steps are repeated until the cluster becomes stable, or a predetermined maximum number of iteration is reached. So for example, if you move towards this one, now what will happen is that this center point is changed in an observation to these big circles or big values are reduced so that the nearby values come into under the umbrella of the center points. So these are the steps that can be repeated multiple times and with multiple iterations to be used. So there are some evaluations that we will do in the clustering model, because since there are no known labels what we will be comparing, but based on that we can matrices, we can calculate average distance to the cluster center, which means how close an average each point in the cluster would be. The average distance to the other center is the distance between each point of cluster to the centroid of all other clusters, as well as the maximum distance of the cluster center as well. So next would be we will be going to the going through deep learning. Deep learning is an advanced form of machine learning that tries to emulate the way human brains learn. So it is it's basically a creation of a neural network that simulate activities based on the actual process of how human brain works. So it's basically showing the network or the network of thought process of the brain itself and replicating into an artificial neural network, which is each neuron is a function that operates an input value and weight, the function wrapped in an activation function that determines whether to pass an output or not. So in this understanding of the deep neural network, the penguin identification classification model, uh, which is done through the machine learning, and what we have done is the specific measures are calculated, which the classification or the penguin class is belong to as a prediction. In other words, the y is the vector or the array of three probability values, which consist of 0, 1, and 2. So we go through the process, and if we go through the process, some of the steps like the following x vector is used as input, and the function of the first layer of neuron each calculate a weighted sum of combining x value and y weight, and then the results are fed forward through the network until they reach an output layer. The output layer actually produces the vector values, which can be evaluated as an element of probability. So in this case, so for example, in this case, there are some inputs, and then the functions is repeated and interconnected with the weight, and then it predicts that this first, it belongs to the probability of this, input, or the height will belong to the group one of the penguins. So, just moving forward in terms of exploring the training process. The training and validation data sets, works in an input layer where we have done all the inputs. The neurons, or the second layer, apply their weights, which are initially assigned randomly, and feed the data through the network. Then we move on to the output layer, produces a vector that, or a list of array that contains calculated values. And then, we also include a loss function to compare the predicted value versus the known value, to aggregate the differences, which is known as the loss. So, for example, if the known class of the case that returned the output in the previous step is, zero class, or the, class one class, then the y should be between 0, 0, 0, and, the three values would be 0, 1, and 0. So in reality, the loss function is calculated, the aggregate to aggregate the variance for the multiple cases and summarize it as a single loss value. And since the entire, network is essentially, one large function, an optimization function is also, used to, get up the each weight of the network loss, as well as how this can be adjusted based on, up to reduce the amount of overall loss. The specific, optimization technique can be, very variable based on the need, as well as the, the increase of the weight and decrease of the, weight also comes up with the within the functions we can do. This function is, this weight is, reevaluated, adjusted, increase, and decrease. This is a bit of a complex process, but, this is just a concepts that, how the process works, and, you don't have to worry about any sort of, in-depth knowledge about how we assign the function, how we do that. And then we can, the machine learning algorithms, or the Azure machine learning, can handle these kind of data itself, to optimize, and to, give a back, to minimize the loss as well. So we've used the concepts to in the Azure machine learning to prepare the data modeling, as well as training and registering and deploying the training model as well. So in order to do that, it comes up with the, with the automated machine learning jobs, which runs, pipelines, as well as the inputs that it takes. So for example, we assign some weights, we assign some prediction values as well, and we give an input, and then, this auto ML will work multiple training jobs with different algorithms and parameters to find the best model itself. Um, It also supports visualization, and, and to visualizing and evaluating the metrics as well. So it gives an end-to-end life cycle of machine learning, projects. This is basically, going through. This is basically a screenshot of Azure machine learning, where we need a storage account, containers, as well as some virtual machines. It is, it is done in the machine learning workspace, where we can which you can provision in the Azure subscription, as well as some other resources, like, storage account, virtual machines, as well as container registries, which are automatically calculated. And these are the, for example, the penguin examples. Once you have, provisioned the machine learning algorithm, or, the system, so we just import the data, we create the computing resources, the running the notebook as well, and then we also visualize, to create jobs and pipelines, and then automated machine learning will determine the train model, and then, give a suggestion on what is, the data is actually. So it's showing accuracy, as well as the area under the curve, as well as average precision and F1 scores as well automatically. So you just need to put a, automation, or, import the data itself in the system. So this is it from this part of the video, and it will be a continuation of the series, where we'll go through the AI services, Azure AI services, as well as the other modules related to computer visions, as well as the fundamentals of natural language processing, as well as generative AI as well. So make sure to follow along, and don't forget to like or subscribe, and also provide me feedback, and I'll be happy to, help you out in any questions related to that. Thank you so much for your time.